good. How are you?
All right. So yesterday we did a little bit more with derivatives. Okay, finding the derivative using that special limit. We even took it a step further and found the equations of some tangent lines, aka touching a graph at one spot. On page 96, I know we finished the two boxes, but I did want to take just a second to kind of show you graphically, okay, using a calculator perhaps, how you can check or verify your work. For instance, how do you know that this is the correct equation that you found? So we're going to take a second and just look at this on a calculator, okay? Now, yesterday we left, I think, our equation in point-slope form. Was that right? Okay. You could turn it into slope-intercept by distributing in that slope and then moving that point value to the other side. If you did that, you would eventually get this slope-intercept form equation. Okay, so what we're going to do is we're going to try to see, is this the correct equation for the tangent line? Does this line only touch the graph of the square root of x plus 1 at this x value of 7? Does it touch there just once? Okay, the definition of a tangent line is touching a graph at one spot. So we're going to graph the original function, and we're going to graph our tangent line that we found in y equals. If you have anything in there, go ahead and clear them out. We'll type in the square root of x plus 1. And we got to be careful with the linear function here because we have some fractions. We'll put those in parentheses so our calculator knows to do those divisions individually. Before we hit graph, let's go ahead and change our window. That way we can see the correct location that we're interested in. Notice how we want to use this x value of 7. So it really doesn't matter what your x min or x max is as long as 7 is found in between those values. So what do you want to use as the x min and x max? It really could be anything as long as 7 is in between them. Do you want to use like 5 and 9? 5 and 8? Whatever. We'll do 5 and 9. Maybe we'll count by ones. Okay. Let's go ahead and think about the y values. Okay. When we plugged in 7 into the function to get the point, aka y value, we got a y value of 3, right? So again, the y values or min and max don't really mean anything as long as 3 is in between those. So maybe we'll do 0 and 5. Okay, it could be anything you want. And we'll count by ones. Okay, so let's go ahead and hit graph. There's your square root. And it graphed the linear one too. It's hard to distinguish between the two of them, right? Maybe we'll zoom out a bit. Okay, let's go to our window. Let's go a little bit less than 5. Maybe we'll do 0. And we'll go a little bit more than 9. Maybe like 15. And we'll still count by ones. You want to do the same thing for the y's? Maybe we'll do, I don't know, -3 and 10. We'll zoom out a little bit, counting by ones. There's our square root. And there's our linear. Kind of hard to tell, right? Because they're so close together, okay? But notice how at that location, okay, they are different, and they do start to be a little bit different up there. And if you were to guess about where they might touch once, okay, using that trace button, it looks like somewhere there in the middle, because it's kind of less bolded. Does that make sense? That they're more on top of each other, touching each other at that spot. So we'll have around that x value of 7. It seems to be checking out. Okay, maybe this one will be a better example. Let's go ahead and try that one. Let's see, our equation from yesterday was y minus 1 equals negative 1/3 x minus 1. If you change that into slope-intercept form, distribute in the slope, move over the point. All right, so in y equals, let's go ahead and type in the original function, 3 divided by, you got to put x plus 2 in parentheses. And then in y2, we'll put in our tangent line. Let's just go ahead and hit graph and see if that'll work for us now. We might have to change our window. Oh, that's a little better. Okay, so let's go ahead and check this out. Let's go a little bit more negative on the x-axis. So we'll do maybe negative 5, maybe even 10. That's a good example. All right, so you have the function, which is the curve, and then there is the tangent line equation you found, okay? If you were to hit the trace button and kind of move that cursor to where it looks like they're intersecting each other, it looks like that might be around the x value of, it looks like it'll be around the x value of 1, okay? And that's where we were checking right there. Okay, so notice how the tangent line is just touching the curve at one spot, and that's at the location that we found based off the problem. Okay, so you can check it graphically if you wanted to. I hope we realize that if the tangent line showed up here, we did something wrong, right? Because that's no longer tangent. Isn't that secant, right? Wouldn't you be touching this point and this one? Okay, so tangent is just touching once at one particular location. So you can probably use your graphing calculator to confirm it if you wanted to. All right, we're going to do a little bit more with derivative today. We're going to take a look at a different technique to help us find a derivative, more specifically at a point than just an equation like we were doing yesterday. So up to this point in this section, we've dealt with a quadratic equation and we did a square root equation. These are the same ones in your notes from yesterday or the day before. When we found the derivative of this quadratic using our limit definition, we had negative 2x minus 4. Okay, that's previously found in your notes. We're just referencing it now. And when we found the derivative for this square root, I think we did that one yesterday, we had 1 over 2 square root of x plus 2. All right, let's go ahead and find the value of f prime, aka find the value of the derivative, find the slope at this indicated x value. So if we were to plug in negative 1 into our derivative equation, what would we have as the slope at that location of negative 1? Can we calculate it? Negative 2 times negative 1 minus 4? We get negative 2. Okay, so graphically speaking, at this x location, the slope of the tangent line is negative 2. Okay, your line's kind of going down, aka slope is negative. Let's check out the other one over here. If you were to plug in 7 into this derivative for the square root, see, we would have 1/6. Is that right? Okay, so up to this point, we've been finding slope values by first finding the derivative equation and then plugging in a number. You see how that's kind of a dual process? You first find the derivative equation, and then you plug in whatever location or point you're interested in. We're going to take a look at something slightly different today. Okay, we're going to take a look at a new limit. Notice how that's up here. And if we really were to think about what this limit is telling us, okay, let's say, graphically speaking, I'm going to draw a little picture over here to the right, kind of like the one we used for the tangent line or derivative example. Let's say that our tangent point right here, we know has an x value of a. What would the ordered pair look like for that tangent point? Can we label it? What would the x-coordinate be? What would the y-coordinate be? What do you think, Dan?
A.
Uh-huh. That's the x-coordinate. And then if you plug in a into whatever function you're working with, it would be f of a, would be your y value. Yep. Okay. Now in our tangent line little drawing here, we also picked some other value over here, right? Okay. We don't know where this location is, so maybe we'll label that x. What would the ordered pair of that point be on our curve? We would have x comma f of x. If you were to draw a secant line through those 2 points, you could do that. And notice how if you move the x point closer to the a point, the secant line would eventually become the tangent line. Okay, that's what we were looking at a few days ago in terms of derivatives. So notice how with these two ordered pairs, do we see them showing up in this new limit here? Don't we have some y value minus a different y value over its respective x minus the other respective x? Do you see that based off these points? So what is this representing? If you have difference of y's over difference of x's, change in y over change in x, it's a slope. Okay? More specifically, if x is approaching a, if you let this x value get closer and closer to a, doesn't the secant line become the tangent line? Wasn't that our idea the other day? I know we had h, okay, but in this case, we are using the idea that we know a specific spot. Okay, we know what this number is. So this is essentially finding the slope at one point, aka a derivative. And the difference with this one is we know which point we want. Okay, where a is that special value of x that you're trying to evaluate. For instance, -1 and 7 in these cases. So we're going to take a look at what this limit gives us in terms of the slope at one point, aka the derivative. Let's go ahead and check it out. The limit as x approaches, we're going to let a, in this case, be -1. Let's see what this limit's telling us to do. If you take a look at the first piece, we need to write down what f of x is. Notice how that's your original equation. And then we have to subtract f of a. What's that telling us to do? If you take a look at the limit, a is the number that your x is approaching. So what do you think f of a is telling us to do? What do do you think, Dan?
Put 1 into the equation.
We're going to put -1. Okay, we're going to take that a value of -1 and plug it into the original equation. So can we do that? Let's see, -1 squared is +1. We have a negative out front, which would change it to a -1. Then we have a -4 times a -1, which would be +4. So we have -1 plus 4 plus 1. Looks like that would be 4. So we have to subtract that value of 4. And it's all over the difference in the x's. Okay, x minus the x value you are approaching, that a value. So if we take x minus -1, that would change to a plus. Let's go ahead and simplify this limit. -x squared minus 4x minus 3 all over x plus 1. Where do you guys feel like going from there? Anything popping out at you? Yeah.
You could factor the quadratic.
Okay, let's go ahead and factor the top. So how do you want to do that?
You could.
Can we pull a negative out first, maybe?
Yes.
Okay, so if we pull a negative out, that'll change all the signs to be positive. So let's think about maybe two numbers that multiply to a +3 but add to a +4. Now that those are all changed. Two numbers that multiply to +3 but add to +4. 3 and 1. Okay. Anything going to happen?
Yes.
X plus 1's cancel. All right. So after the cancellation, let's go ahead and try direct substitution for our limit. If we plug in -1, -1 plus 3 is 2, but negative out front gives us a -2. Coincidence that our derivative value was -2 from the middle section? I think not. Okay, we're going to investigate that idea. Okay, so this new limit we have here is still a way for us to find a derivative, okay, find a slope, but what's different about it is we are specifically finding the slope at this point. Okay, when we did the derivative for this function the other day, we came up with this equation. So this equation is representing at any point. Do you see the difference? When you have an equation, you can choose any point you want to plug in to find the slope. What this new limit is telling us, if you only want to find the derivative at this spot, maybe you only have to do one limit and boom, there's your answer. You don't have to do that double dipping. You don't have to find the derivative and then plug in the point. Okay, you can just find a limit and you're done. Okay, so we have this kind of alternative way to find a derivative, but this one is only used when you know a specific spot. If you don't know a specific spot, that's when we're going to figure out the function, because we could use any spot we want if that was the case. Okay, let's try another one here. The limit as x approaches, in this case our specific spot of interest was 7. So based off this new limit, we're going to take the original function, which was the square root of x plus 2, and we're going to subtract f of a. So we got to take that a value of 7, plug it into the original function. Looks like we get 3. And this is all over x minus a, which would be the x minus 7. where do you guys want to go through to help, or what do you guys want to go through to help us solve that limit? Anything popping out at you as a clue that we have to use? Yeah.
Multiply by the conjugate.
Let's use a conjugate. All right, so this would be x plus 2 plus 3. We're going to multiply that on top and bottom. If we multiply it up top, the square roots would cancel each other out, so we're left with just x plus 2. When you use a conjugate, the outside and insides already cancel each other out, so there's no need to actually show that work. The last terms, though, we have negative 3 times positive 3, which would be a negative 9. And that's all over the x minus 7 that was originally in the denominator, as well as the conjugate that you need to multiply down there to keep your fraction balanced. Okay, so we multiply this up top and down below. Anything going to happen? Notice up top we have plus 2 minus 9, which would be minus 7 if you simplify it. So x minus 7 up top, x minus 7 down below. Right? Wouldn't those go away? So we're left with 1 over this conjugate. If we did direct substitution, okay, plugging in that 7, let's see, 7 plus 2 is 9, square root of 9 is 3, 3 plus 3 is 6, we'd have 1 over 6. Notice how that's the same exact derivative value we got before, right? Just instead of finding the derivative equation and then plugging in 7, we just simply had to solve one limit, and we get the same result. Okay? I'm not saying that this is what we're going to use all the time, okay, because we're eventually going to start talking about some shortcuts, some simpler ways to find derivatives, but I wanted to at least show you guys this because it is an alternative way to find the derivative at a point if you know the point you're interested in. Okay, so just to make note of that, we'll say this limit represents the slope of the tangent line, aka derivative, at a specific point. Okay, whatever that a value is. So if I told you to find the slope at 2, you could use this limit where your a value would be 2, because you know what that point is. If I told you to find the slope anywhere, okay, you would have to use that other limit that we were doing yesterday, because you'd be left with an equation that you could then use to find the slope anywhere. So there's a difference between the two, okay? We're going to make note of that on the back page, okay, because we have these two limits. They're both representing a derivative, but it's how they find a derivative that's different. Okay, so the first one is the big limit that we were working with yesterday. The other limit, our alternative form, is this new one. Okay, so if you were to use the first limit, okay, you'd be left with a function, aka equation, that can be used to find the slope of the tangent line at any point. Okay, so whenever you use that first limit definition, you're usually left with an equation. Okay, there's some x variable left over. But notice how when we used this limit in the last two examples, didn't we have a number left? Okay, if I flip it for a second, weren't we left with -2 and 1/6? Those are no longer functions. Okay, those are values. Those are numbers. So this limit is going to give you a value that represents the slope of the tangent line specifically, if I spell that right, are there 2 L's? Specifically at the x value of a. They're both limits, they're both representing slope, but they yield 2 different results. Okay, the one limit gives you an equation, okay, a function that you can use for anything. The other limit is giving you a number, okay, which represents the slope at one point. You would have to repeat the process if you wanted to know other points, okay, and if that was the case, probably using the first limit would be the better option, because if you can get an equation that can be used for any point, you can just plug in those points and figure out those slopes. Boom, 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 boom. So there are some pros and cons to each, but we need to know the difference. All right, short day. We'll do more derivatives tomorrow. Me too. You too.